Well, today we are going to prove a theorem from linear algebra. The theorem states every square matrix can be uniquely represented as a sum of symmetric and skew symmetric matrix. And this representation or decomposition is unique. Well, let's say that we have a matrix A, or better, we have a matrix B, which equals A plus B, such that A is symmetric and B is skew symmetric. Now we know that for symmetric matrix, A is equal to A transpose, right? For skew symmetric, B is equal to minus B transpose. This we know. Now, if we if we rewrite equation 1 as B equal to A is equal to A transpose and B equal to minus B transpose. And then let's say that we sum up these two equations. So it will be like 2P is equal to A plus B plus A transpose minus B transpose. And then we can rewrite it as B is equal to 1/2 of A and rearrange the terms A plus A transpose plus 1/2 of B minus B transpose. So now we have a term here, A plus A transpose and B minus B transpose. Now we need to prove that A plus, well, we can ignore the constant 1/2 here. We need to prove that A plus A transpose is symmetric and B minus B transpose is skew symmetric. Let's say that this A plus A transpose equals X, and let's take transpose on both sides. So A plus A transpose is equal to X transpose. And then if we simplify it, let me actually rewrite. A plus A transpose is equal to X, and then A plus A transpose is equal to X transpose. And then if we simplify it further, is A plus A transpose plus A is equal to X transpose. So if you look at X and if you look at X transpose, they are both the same. So X is equal to X transpose. Thus X is symmetric, which means that A plus A transpose 1/2 is symmetric. Now similarly, we can prove that B minus B transpose is skew symmetric. That Y is equal to B minus B transpose, 1/2 can be ignored again. So if we take transpose again, Y transpose is equal to B minus B transpose, whole transpose, and then Y transpose is equal to B transpose minus B, which can be rewritten as minus B transpose. So now if we look at Y and Y transpose, we can clearly see that Y is equal to minus Y transpose. So 1/2 of B minus B transpose is skew symmetric. Thus, every square matrix can be represented as sum of symmetric and skew symmetric matrix. The problem is we have to still prove that the decomposition is unique. This decomposition is unique. This means that this X and Y is the last pair of the universe, or there does not exist any pair such that x1 plus y1 is equal to p. Let's assume that there exists another pair of matrices T and N such that T is symmetric and n is skew symmetric, which means then x plus y is equal to t plus n, right? Let me rewrite it again. X plus y is equal to t plus n, which means x minus t is equal to n minus y. But we know that x is symmetric and t is symmetric. So the differences of a symmetric or matrix is still a symmetric matrix. So this has to be symmetric, x minus t. And this n minus y, we know that difference of skew symmetric is skew symmetric. Skew symmetric. Let's say that x minus t is equal to, I don't know, maybe s, and n minus y is equal to something r. So this means that s is equal to r. So we need to, we want to think of a matrix where s, which is both symmetric as well as skew symmetric. It turns out that the only matrix that is all skew symmetric as well as symmetric is the zero matrix. Thus, s is equal to 0 and r is equal to 0, which means n is equal to y and x is equal to t. Thus, the decomposition is unique. And if there exists any other decomposition, it has to be equal to this decomposition.